Hello, welcome to Lecture 17 in this series intended for a flipped Introduction to Proofs course. Uh, Today we're going to be covering section 3.4 from A General Introduction to the Art of Mathematics. And this section is about disproof, the opposite of proof. Sometimes you're disproving things. We'll spend kind of a lot of time, really. In fact, in a sense, the main point of this section is to develop a better facility with kind of a BS detector, recognizing when statements are wrong. And so, yeah, distinguishing true from false. Then we'll actually look at a bunch of examples of statements and disprove them. Occasionally, I'll mix it up so that there's two statements, one of which is true and the other is its negation and it's false, and you've got to figure out which is which. Let's get rolling. So, yeah, you need to develop a good lie detector. That's really sort of an essential component of of getting through a course like this for sure, but also becoming a mathematician. You you want to look at a statement and go, I don't think so. For instance, I think I've remarked a couple of times that when somebody tells you they found this interesting pattern in the prime numbers, something to do with primes, it's hardly ever right. It's really just people haven't explored far enough to catch where the pattern fails. Um, Not that there aren't patterns in the primes, but they're not easy. Um, so the best way to do this, to detect when something is wrong, is to play with things. And I think students are often really um, reticent about doing that. It feels strange to just start plugging in numbers and playing with things because you're used to having true sentences handed down to you from your teacher, and you were asked to memorize things, and so that's true. But that's not the way the real world works. You're always a little bit at sea. What is in fact the true sentence? What is not? So you've got to be the person who's willing to explore a little bit and figure out which. Well, there's a good point. Suppose you're on a test, and this is what I do on my tests. I say prove or disprove the following. And if it's a false statement, the disproof is quick. And if it's a false statement and you try to prove it, you'll be there until the end of the period, not getting anywhere because it's not possible to prove a false statement, right? So you'll be spending an awful lot of time trying to do something that can't be done. That hurts. It really feels bad when you realize you've been burned by that sort of thing. Um, so yeah, really important to get this facility for detecting false things ahead of time. I mentioned this already. You really have to develop a sense of personal freedom that you're allowed to just explore, see what's going on, see if you can figure out whether the thing is true or not. By what do? You try small values. Stick in different values for the variables, and if you find one where the given statement doesn't hold with those values, then boom, you're done. You've got a disproof. A computer algebra system, that's what CAS stands for. Yeah, definitely. This this is your best friend at these days, right? I feel bad for people like Leonard Euler or Pierre de Fermat who had to work on fairly advanced mathematics without any kind of crutch. Well, we've got them now, so of course use a computer if it's getting too hard to work by hand. All right, so we're going to roll with a couple of examples of things that are not true, but how do you figure out that they're not true? I believe we pointed out that this is not one of the actual distributive laws when we were looking at the distributive laws of in logic of conjunction over disjunction and vice versa. So, in fact, what works with the distributive laws is things distribute over the next thing lower in the hierarchy, like multiplication will distribute over adding and subtracting, as does division. Well, gotta be careful with division. But think of division as multiplying by reciprocal when you're good. And exponents, which includes roots, distribute over multiplying and dividing. But exponents do not skip over and distribute over plus and minus. So this rule, as stated, is false. Trust me on that. Yeah, it's not true. So do you see how I got that slash to appear in there? Yeah, that's not true either. What's going on here is the original statement was false, and when you make an inequality there, or a not equality there, you've just created another thing that's false. If you really wanted to negate that, see how it's universally quantified? The negation of that wouldn't be just putting a not in there, it would involve changing the quantifier to it exists. We're going to play with that a lot. Okay, so here's some exploration that I've done in advance. There's a table with reasonably small values of A, B, and C, and these all work. These all do it. They all the distribution of A over the sum of B and C gives the same result as B to the A plus C to the A. So the first one I have A is equal to 1, B is equal to 1, C is equal to 2. So when you add first, you'll get 2 and 1 is 3, and then raise that to the 1 power, 3. And then when you raise the powers first, it's 1 to the 1 and 2 to the 1, which are 1 and 2, so that's also 3. Here's another one with A equals 1. 1 is the power on 3 plus 4 gives us 7, and 3 to the 1 plus 4 to the 1 gives us 7. Well, you probably see what I'm pulling there, don't you? What's the trickery involved here? It's that the power 1 actually does distribute, because the power 1 does nothing. So it's sort of a trivial version. But we do have examples that show the statement here where it says it's never the case that B plus C to the A is equal to B to the A plus C to the A. That's not in fact true. What have we done in this next one? I bumped the power up because I felt like that was cheap to use a power of 1. Here's a power of 2. 0 and 3 are the numbers. So 0 squared is 0, 3 squared is 9. That's this 9 right here. And then if I add them first, 0 and 3 is 3, and I square that, I'll get 9, and that's that 9. And they're equal. Power of 5, that's even bigger. 2 plus 0 to the 5th power is 32, and 2 to the 5th plus 0 to the 5th is also 32. Well, now what shenanigans is being played here? If one of the numbers is 0, this distribution will work, but again, it's cheap. So that's a lot. We've explored a little bit. We've seen some situations in which this statement actually is true, that you can distribute a power over a sum, but it's not generally the case. So where do you find some values that do provide us with a counterexample to this proposed rule? Well, before we go on, let's stop and think. What could we use? I think anything where A is not 1 and we don't have one or the other of B and C being 0 will do the trick. So the simplest one I can imagine is 2 for the power, and both B and C would be 1. So if we added 1 and 1 and then squared that, we'll get 4, right? But if we square 1 and add it to the square of 1, we'll get 2. There's a case where they're not equal. If we'd taken this table just a little bit farther, we would have found that counterexample. All right, next false theorem to look at. For all integers named A, B, and C, if A divides the product BC, that implies that A divides one of the factors. Either A divides B or A divides C. Let me highlight that as we go through it again. We've got the assumption, or the antecedent of this conditional sentence is that A divides the product BC. And from that, we conclude that one of these two is true. Either A goes into B or A goes into C. Seems okay. Actually, it feels like that there's something to that. It feels like maybe it's true. Oh, shoot, not true. So that's also not right. I can't just put a doesn't imply. I really need to change the quantifier to existential. But so anyway, here's another big pile of misleading evidence. Okay. Wow, there's a lot of it here, though. I seem to be looking at mostly random-looking numbers here. So let's see, A is 2, that's good. We're basically asking, is the product even? Does 2 divide into BC. Well, if B is 7 and C is 6, that's 42 is the product. Does 2 go into 42? Of course it does. And does 2 divide either 7 or 6? Yeah, it divides 6. So the or statement is true. Right? Does 2 divide, if the numbers are 4 and 5, what's this first one going to be about? That's asking, does 2 go into 20? 4 times 5. And it does, so that yes is correct. And is it true that 2 divides one or the other of 4 and 5? Yes, it is. It divides 4. So that yes is correct. Maybe this is like before, though. Is there a reason I'm choosing 2 as this number? Maybe it works for 2, but it doesn't work for other values. So here's 3. Wow, what is 12 times 11? 100 and, let me think about it, 132. Mental arithmetic. 10 times 12 is 120, and 1 times 12 is another 12. So, yeah, 132. Does 3 divide 132? You can do that in your head because you just checked that 3 divides the digit sum of 132, which is 1 plus 3 plus 2. Wait, do it by fingers. 1 plus 3 plus 2. That's 6. Okay, so yeah, 3 divides 132. And is the other statement correct? Does 3 divide 1 or the other of these? Well, I can see that 3 divides 12. It doesn't go into 11, but we just need it to divide one of them for the or statement to be correct. All right, how about 3 divides, what's 5 times 15? 75. Oh, actually, that's easy if you think about money. If you have 3 quarters, 75 cents, can you divide that evenly into groups of 3? Of course you can. So 3 divides 75, yes. Does 3 divide one or the other of those inputs to the multiplication? Sure, it divides 15. 3 times 5 is 15. So that one works. All right, well, maybe it's something to do with 2 and 3 being little. So here's 5. Does 5 divide, what is 4 times 15? That's 60. Time helps you with that one. A quarter of an hour is 15 minutes, so 4 times 15 is a full hour, 60 minutes. So yeah, does 5 go into 60? It does. If each hour gradation on the clock, going from like noon to 1 o'clock, there's 5 ticks in there for the minutes. So yeah, 5-minute intervals, 12 of them makes a full hour. All right, so what did I just say? 5 goes into 60. Yes. Does 5 go into one or the other of these? Of course it does. It divides 15. Looking good. I'm going to stop going through this. What trickery am I pulling this time? Have you noticed? I have only used prime values for A. Only used prime values for A. And it's because this statement is actually related, well, not with the not in it, but it's related to the advanced definition of what it means to be prime. You're prime if, whenever you divide a product, you'll divide one of the factors. So this is going to work for primes, but if you stick in a composite number, it's not. A good little challenge is to come up with sort of a very tiny little example that shows you this is not true, but you don't have to go to very big numbers. What's the smallest composite number you could use? I guess 4 is the smallest composite number. Maybe I would go with 6 because 4 seems like it's kind of a cheat too because both factors are 2. 4 works. You can come up with a counterexample using 4 as A, and as long as B and C are just even but not divisible by 4, you've done it. And in fact, the product of B times C, if both B and C are even, you'll pick up 2 copies of 2 out of them. Each one contains a 2 as part of its factorization. When you multiply, you'll have 2 2s. So 2 2s, like the outfits you wear in ballet. No. So yeah, you could come up with a counterexample with 4 or with 6. You don't have to go hog wild. It's good to find nice, simple counterexamples when you can. For instance, 6 divides 2 times 3, but 6 does not divide 2, and it does not divide 3. That's an easy one. Title of this: Why is he trying to lead us astray? Well, I'm not. I'm trying to get you to become good lie detectors, good people that notice when things are not really correct. So here's a really interesting example of a prime generating polynomial. N squared minus 79n plus 1601 gives a lot of primes, but I've said this a bunch. It's not likely that you're going to come up with a simple formula like that that actually produces nothing but primes. Let's play with the calculator a little bit though on this. Go to y equals, and we will put in that formula. Of course, it'll have x's in it instead of n's, but x squared minus 79 times x plus 1601. Right? And let me check my table setup. We're starting at 0 and we have an increment of 1. That's great. So we'll look at the table. Well, I don't know. That's a problem. I don't know whether 1601 is prime off the top of my head. We do have that primes list, or that table, that one-page sheet that gives all the primes up to 5,000. So you could look it up on there. I did previously, so I'll tell you that is prime, and so are these next several. But you know that all of these are prime. Oh, look at it; they're going down. I'm eventually going to run out of primes because there's only so many below a couple of, what was it, around 700? It started. No, it started at 1601. Wow, they're getting tiny. Oh, here's an interesting thing. Do you see how they came down to 41 and then they began going up again? Well, let's look at the graph. Do you know what the graph of this formula that we just stuck in is? Well, it's not empty, it's just I don't have the right zoom. I think we may have to zoom out more than just once. You know, it might be smarter to just change the window setup. So let's go from 0 to, around where was that place where it made the turning point? I think it was in the 40s. So 0 to 40 should do it. And the x scale, sorry, x scale on these calculators is how far apart the tick marks are. Let's just make it 5 so it doesn't look like we've got a hairy x-axis. If you get too many tick marks on the x-axis, sometimes it ends up looking like a really solid fat line. For y, I think the smallest we need to go is 0, and let's go all the way up to 1601, so we see that one big prime that started out when x was 0. Now we graph. And, all right, wait, what kind of graph are we looking at here? You should know, actually. I'm sure everybody does know. I'm just trying to reveal it a little at a time, but that's silly. If I took this out to twice as far, because we just arrived at the vertex of that parabola, right? Then look at the graph. Sure, it's a parabola. So part of the trickery in this one is it gets you primes from the x value of 0 all the way to the x value of, I believe it's 41. And then you see the same primes again a second time. That's part of what's going on. But it's pretty surprising that you get a sequence of numbers that are all prime. In fact, I think it's like 79 positions in a row where you get a prime. Yeah. So let's not use a calculator for this. Let's look at this on CoCalc. Okay. So this is the spreadsheet the worksheet we were playing with last time. I want to do something in Sage code similar to what I just did on the graphing calculator. So let's see, how will that fly? I'm going to use a loop for I in range 40. Remember that when you're doing a control structure in Sage or Python, you end the line that introduces the control structure with a colon, and then when you hit enter, it'll automatically indent you the right amount. For I in range 40, let's calculate, let's call it y. Will be let's see, the formula was I to the, or x to the second power, minus 79x plus 1601. And what I would like to do is, I guess I'll print I, but I'll also print the y value, and I'll also print the output of the is prime function so that we'll know whether, in fact, that y value is prime. So here goes. We'll print I and y and is. Remember, is prime has an underscore in it. Is prime y. That should do the trick. Oh, I was like looking at all these falses that are coming out of there, and it totally confused me for a second. But there's a typo in what I typed here. See how I was using I as the variable, but then when I think when I jumped over to look at the slide to get the formula, now that has n's in it. I don't know why I put an x, but you see that this should not be an x right there. Now it should do the right thing. I guess the previous value of x from somewhere else in the worksheet was in there. All right, so this is what we were after. 1601, 1523, blah, blah, blah. They're all primes. You see all these trues? Where's that low spot that I was worried about? Because I think it's right there, 30, at stage 39. We're at 41. Let's take the range a little farther. We go twice as far. It's still trues all the way down the line. There's our turnaround point. At 39, we had a y value of 41. At 40, we also had a y value of 41. And then they start increasing. You're going up because of the symmetry of the parabola. You're going up through the same y coordinates that appear at the integer coordinates for x. And then, oh, wow, they were all true. Look at this last one. At 79, we got 1601 again. Well, I don't want to leave you with the impression that this is true all the time. It's true over a remarkably long range, but not that far. So if we go down to the end of my thing again, at 80, we get 1681, which is not a prime number. In fact, that's 41 squared. If you think about that, it looks a little bit like the FOIL ruling of 40 plus 1. Yeah. In fact, you know what is an even quicker way to see that this is not prime all the time? Let's do the range from -1 up to 81. At -1, we'll also get 1681. So if I hadn't been kind of trying to mislead you from the beginning, we might have seen the values at negative values. In fact, we might have seen that on our calculator when I was doing the stuff on the table mode on the calculator. And 1681, well, certainly if you were equipped with that table of primes, you wouldn't be fooled by it. 1681 might fool you as a prime, although I do personally spot that it looks like the trinomial you get out from 40 plus 1 times 40 plus 1. All right, so not a true sentence after all. Let's actually minimize this Sage worksheet. Okay, so let's actually get into doing some disproofs then. First, I think I want to talk a little about the philosophy involved, and then we'll get into the meat of it. The big point is that disproving one statement is also proving something else, right? If you're disproving X, then that's the same thing as proving the negation of X. If you expect to show to me that X is not a true sentence, then I can say, well, very well, then the negation of that is a true sentence. If you are thinking about disproving a universally quantified sentence for all x p of x, well, you're going to prove that, you need to disprove, no, wait a minute, let's be careful. To disprove that, the universal thing, you need to prove the negation, right? And that's existentially quantified. The existentially quantified thing, though, is the negation of p of x. That's actually doable. Find some x that makes p of x not be true, and vice versa. Now this is the other side of the coin. I didn't put it in here in statements, but if you're trying to disprove an existentially quantified sentence, then you need to prove the negation, and that'll be universally quantified. So let's just tie all this together. If you're disproving an existential, it's just a regular old proof. It's the kind of things we've been doing in direct arguments where we're proving universals. And disproving a universal, that's finding an example. That's proving an existential. Just the role the thing is playing in this process is a little unusual. It's not truly an example. It's an example of not, the thing not being true. So it's called a counterexample, a word that I've already used freely in here, and I think people are familiar with. Just, I don't know, beating a dead horse, I suppose. Okay, so here's an example. Remember how we checked out whether p sharp plus 1 was always a prime on Sage? So here's a theorem. It's not a true theorem, but here's a theorem. For all p in primes, p sharp plus 1 is prime. And that is a complete disproof of it. You just say, boom, this statement is false. A counterexample is p equals 13. Since 13 sharp plus 1 is 30,031, and 30,031 is 59 times 509, which is composite. Now, that's a little wordy. If it would actually be perfectly good to just say a counterexample is p equals 13 and put a period there. A lot of people will do that. I tend to be, maybe you've noticed, I get a little pedantic. So I like to start out by saying, absolutely, unequivocally, the statement is false, so that I'm making it clear to people that I'm not trying to prove something that's wrong. Say it's false, give the counterexample, and if the counterexample's verification is something that you're going to force other people to go off and log onto a computer for, and you've already done that work, isn't it just sort of kind to show them the work you've already done? So you don't have to be this verbose, but I think you can view it as an act of kindness in certain regards. It's also a lot extra detail that some people may not want to know. They might go, oh, there's a counterexample. Fine, I can move on from that. Okay, here's another example of a proof, or actually a disproof. We'll talk about a little language so that you understand what the statement is. If you have a sum where the signs of successive terms are always opposite, so it goes from plus to minus to plus to minus to plus to minus, or minus to plus to minus to plus, that's called alternating. So here's an example. 1 minus 4 plus 9 minus 16 plus 25 minus 30. I'm alternating sum of squares right there. But the point is simply that it's an alternating sum. You may have run, if you've taken Calculus 2 or Advanced Calculus where you deal with sequences in series, you'll have run into alternating sums before. So we're going to let A of n be the alternating sum of factorials, starting with n factorial and actually descending. So it's going to start at n factorial and go down until we get to either plus 1 factorial or minus 1 factorial. You can't tell in advance whether it's plus or minus because it depends on the parity of n. I'm not sure which way it works. I think if n is even, it'll be negative, and if n is odd, it'll be positive, but I could have that wrong. All right, so I should probably label this with conjecture since it's actually not true, and it's sort of bad practice to label things as theorems that aren't true, but we're going to later disprove it, so that's fine. For all n in Z, if n is greater than 2, then A sub n is prime. Well, yeah, of course, we're going to use Sage for this. Let's pull up that Sage worksheet, and I don't really. There's a nice little trick of the trade with Sage. You just see how line 33 has this little triangle with it? That's showing that the line 33 is expanded. If you click on that, it hides all that. So if you want to quickly get rid of a whole bunch of output that you don't really need to be seeing, clicking on those triangles is a good thing. All right, so I want to first do up a little Sage function that creates the alternating sum of factorials. We'll do that with the def function, the def keyword, define a function. And I'm going to call it ASF for alternating sum of factorials. It's going to have an input, let's call it n, like it was in the slide. And everything after this colon is going to be inset. That'll be the body of the definition of the function. Well, what are we going to do in the body of this function definition? I'm going to be a bad boy, by the way, and leave out the documentation string here. So we're just going to start coding and not worry about telling people what this function is for, even for telling ourselves what this function is for, because it's a throwaway. We're going to use it once and get rid of it. But what's going to need to happen? First, there's going to be a sum of alternating factorials that we're going to want to end up returning. So I'm going to call that S, and let's start it with a 0 in it. And then we'll have a loop. The loop variable I'll use I. So for I in range n. But I'm going to actually do something a little funky. With the number that the factorial that we'll be adding on will actually be n minus I. So the loop is actually taking us sort of, well, the way that we described it in the presentation, in that direction. We're starting with n factorial and then dropping. I could write this in such a way that it would do a range that started at n and went down through different values, but it's simple enough to use range n. And then need to have a colon, and now that stuff will be intended. So we're going to add something to S. There is a short circuit operator or shortcut operator called the plus equals operator, which says take whatever is after it and add it on to the whatever's currently in the variable S. So S plus equals, we want the factorial of n minus I. So the first time through that loop, I will be 0, and we'll be putting factorial n in. And then each successive term we want to either add or subtract. Now, how do we make it add or subtract? That's a fairly common trick. Again, if people who took this kind of stuff in Calc 2, you'll recognize it. You put minus 1 to a power. And in fact, we want the ith power. And then you multiply that. See, minus 1 to a power, well, you'll get negative 1 whenever the power is odd, and you'll get plus 1 whenever the power is even. So this is going to create the alternation we want. And when we want the first one, which is encountered to be minus 1 to a even power, and it is because of our range operator. It uses 0 through n minus 1 as the range. All right, so that should do the trick. Once we've finished executing this loop, we'll have S. What did I just do that for? Sorry. I hit a return with my cursor in a place I didn't want it to be. So we're done with the loop after that, and we will then return a value of S. Now, I think this is good, but you never know. That's the first check. Execute the def command and see if it coughs up an error. It didn't, so that's a good sign. The other thing we might want to do is check it out for some small values. ASF of 3, what should that be? That's 3 factorial minus 2 factorial plus 1 factorial. 3, that would be 6 minus 2 plus 1. Did I just do that right? 6 minus 2 plus 1, like that. That's 5. What about ASF of 4, just to push our luck a little bit? 19. Now that should be 4 factorial is 24, right? Minus 6, we'll just have to change these signs now. Plus 1, plus 2, and then minus 1. Yeah, 19. So that's enough checking. I believe it now. All right. What the theorem we were asked to look into, the conjecture really I should have called it, is that when n is bigger than 2, an is prime. So let's get the computer to tell us about the primality of a sub n for n equals 3, 4, 5, etc. I'll use n as the loop variable this time. N in range, I just want to go to 8, I think. No, actually, I don't want to go range 8. That would give me values where it's not going to work. So let's start at 3 and go up to 8, range 3 to 8. Well, why did I hit enter or shift and enter? I wanted to just hit plain enter. Now that error bar staring at me bothers me, but that'll go away as soon as we actually execute our code. Let's see, let's call it, there won't be any name conflict, but I just out of force of habit, I'm going to call it little s is the sum. Little s is going to be the alternating sum of factorials with n as input. And then on a line here, we're going to print n, s, and whether or not s is prime. Right? That's all I want to have happen. So when n is 3, the alternating sum of factorials is 5. Well, you see all the trues there. We got true, 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 true. And the numbers, well, I wouldn't want to do them on my graphing calculator by hand. They're getting big. But that 8 that I put in there was very carefully chosen. No, it wasn't that carefully chosen. Apparently I should have put in 9 but if we go one more step, we'll find one where it's false. And if you want to write up a disproof of this, you'd kind of like to know, to be able to justify that 326,981 is in fact a composite number, not prime. Yeah, it's 79 times 4139. Okay. So that's our exploring in Sage. Here's the formal disproof for this statement. The statement is false. A counterexample is n equals 9, where the alternating sum is, I cheaped out, I guess, and didn't want to write down the entire alternating sum. But anyway, the value of it is that number we found, and that factors is the factorization we just found. So, like before, you could just write a counterexample as n equals 9, and that would be a complete disproof. I feel like there's a little bit of kindness to your readers is to explain to them why that's a counterexample and not force them to go off and verify it themselves. But, actually people who are reading mathematical proofs and disproofs are sort of expected to verify a lot by themselves. So that's not totally unreasonable. And again, I like to lead in with a clear statement that the thing is false. Okay, we're going to do one last little exploratory thing where I've got two statements that basically are alternate possibilities. One might reflect reality and the other be false, or vice versa, because they are negations of one another. The sum of any two irrational numbers is irrational. On the face of it, that sounds pretty plausible because that's one of those closure axioms, right? That you could have the set of irrational numbers is closed under addition, is what this would be saying. And then here's this other sentence, which is, do you see this as the negation of it? I should point out something here. This sentence does not have a clear quantification status. Does it? Or maybe it does. Yeah, I think that word is what makes it clear. Any two irrational numbers. So that's indicating a universal quantification for it. Any pair of rational numbers, you add them up, you'll get an irrational. I think I just said it wrong, didn't I? The sum of any two irrational numbers is irrational, universally quantified. And then this one very clearly is existentially quantified. Comes right up front. There are two irrational numbers whose sum is rational. Well, what do you think about that? Which one is real and which one is fake, false, wrong? Probably a little bit surprising, it's the first one that's wrong. And let me say why. And there's a hint. If a number is irrational, isn't its negative also going to be irrational? You see why that's such a good hint? It's huge, right? Okay, well, to put it that way, here's the real deal. The sum of any two irrational numbers is irrational. No, This statement is false since root 3 and minus root 3 are both irrational, but their sum is 0, and that's clearly rational. Every integer is rational. So there you go. That was the false one. Theorem, there are two irrational numbers whose sum is rational, because this is what we found here. Root 3 and minus root 3 are the two that we could say. I chose to prove this theorem, which is existentially quantified, using a different pair of examples. 1 plus root 2 and 1 minus root 2. Those are both irrational numbers. You can go in Sage or even on your graphing calculator and see that their decimal expansions have no discernible pattern in them. And in fact, we can prove that the sum of a rational and an irrational is irrational. So I know both of these are irrational, but their sum would appear to be 2, right, which is definitely rational. A final little word of caution about this stuff. We just proved something by providing an example. That very, very seldom happens, because think about the kinds of statements people are interested in proving. We hardly ever want to prove something that's existential. We look, most often we prove things that are universally true. We wouldn't bother with writing a proof of something unless it wasn't, a powerful statement that was true most of the time, all of the time, preferably. So why did that work in the last example? Well, we were in this unusual circumstance of proving an existentially quantified sentence. So fine, there you can provide an example. Let me just point out the contrast, though. Disproof, by coming up with an example, we do that literally all the time, because the statements we're looking at are typically universal, and we disprove them by just finding one example that shows the rule isn't true all the time. Proof by example, on the other hand, is so uncommon that people use that as a criticism. What are you trying to do, proof by example? Because a lot of people do, right? People who haven't got much mathematical training do it all the time. They try to wow you with a preponderance of the evidence, and a math person just sits back and goes, that doesn't convince me at all. The first counterexample might be somewhere off in the billions. Yeah. In fact, that indeed happens. So we've come to the end of today's slides. I'm afraid this is a little bit of a short lecture, but some days you win, some days you lose. The next section that we'll be covering is 3.5, which is about a couple of important techniques for proving things. Proof by dividing the world up into a finite number of cases, and what's known as exhaustive proof. Occasionally there are situations where you just have to check every number in some range and verify that a thing is true, literally by exhaustion, checking it over some. Of course, there will always be a finite universe. You can't check everything in an infinite universe. So, but if you're in a finite universe, and there's real math that takes place in finite universes, you can do exhaustive proof. Well, that's for next time. Please take a look at section 3.5 in a general introduction to the art of math, and have a great rest of your day.